What can derivatives tell us about whether a function is increasing or decreasing? Increasing and decreasing officially means that, for example, if you are increasing, then your y value is bigger when your x value gets bigger. So if we had a picture of this, here's x1, here's x2, you're officially increasing if f of x1 is smaller than f of x2. Similarly, you're officially decreasing if f of x1 is bigger than f of x2. But we don't want increasing or decreasing for individual points. We want to be able to say something about an interval as a whole. So this definition is really saying if for all points x and y in an interval, this is true, then f is increasing or decreasing on that interval. That's a really hard thing to check. So what we'd love to be able to do is use derivatives to tell whether an interval is increasing or decreasing. And we can do this, it should make good sense. If the slopes of the tangent lines are always positive, the interval is increasing there, and if the slopes of the tangent lines are always negative, the interval is decreasing there. And that is what our test is going to say. Now this is actually a kind of an important theorem in math. You have to use the mean value theorem to show it, which I'm not going to do right now. But it's not obvious that these two definitions on this page are exactly the same, but it turns out that they are. So how do we use this? If we want to find intervals where a function is increasing and decreasing, well, we need to know when f prime is positive and when it's negative. This is actually not too hard to check, as long as we have a function f prime that's continuous. So let's find our function f prime. This is going to be 12x cubed minus 12x squared minus 24x. And this is a polynomial, so it's continuous. Since it's continuous, that tells us it can only ever change signs if it's equal to 0 or it's undefined. It's because it's continuous on its domain. So this function is in fact never even undefined, so we only need to figure out where it equals 0. So let's factor it. Let's factor out an x, and we can also factor out a 12. So we're left with x squared minus x minus 2. And let's see if that factors. So we need two numbers that multiply to -2 and add to -1, and that would be -2 and +1. So this tells us 12x equals 0, or x minus 2 equals 0, or x plus 1 equals 0, which means x equals 0, x equals 2, and x equals -1 are our critical points. These are the places where the derivative equals 0. So now we can make an f prime number line. So we're going to make a number line like this. We're going to put all of our critical points on this number line. So we have -1, 0, and what we have here is 2. And we know that on each of these intervals here that f prime cannot change sign. So we just need to figure out what the sign is on each of these intervals. And the way we're going to do this is by plugging in test points. Since we know that the sign is the same in all of these places, we'll plug in any point we like, really, in each of these intervals. So I'm going to plug in -2, -0.5, 1, and 3. Notice that the function I'm plugging these into is f prime. We want to know what the sign is of f prime. So if I go ahead to try to figure this out, I know f prime of 2 is equal to, I've already factored f prime, so that's going to help me. It's 12 times 2, oops, -2, right? 12 times -2 times -2 minus 2 times -2 plus 1. And now I can look at what the signs are of each of these factors. So we have a positive 12, a -2, a -2 minus 2, and a -2 plus 2. So if I multiply one positive and three negatives together, this is going to be a negative sign. So that means that f prime is negative all the way from negative infinity up to negative 1. Now we can do the same thing for f prime of a half, of negative a half. So I'm going to have 12 times negative a half times negative a half minus 2 times negative a half plus 1. Now this one, most of these terms stay the same. Positive 12, negative a half, negative 2.5, but now we have a positive for the last term because negative a half plus 1 is a positive number. 2 negatives and a positive and 2 positives gives us a positive sign. So we know that f prime is increasing, or is positive. F prime is positive and f is increasing from negative 1 to 0. Now we're going to do f prime of 1. That's going to be 12 times 1 times 1 minus 2 times 1 plus 1. And now one more of these terms is going to change. 12 is positive, but now 1 is positive. 1 minus 2 is still negative. 1 plus 1 is positive. So this now gives us one negative sign. So this is negative again. So now we know that f prime is negative from 0 to 2, or f is decreasing from 0 to 2. The last one to check is f prime of 3. And this is 12 times 3 times 3 minus 2 times 3 plus 1. And all of these terms are going to be positive. So 4 positives gives us a positive. And that means that f prime is positive from 2 to infinity, or that f is increasing from 2 to infinity. So writing our final answer in terms of interval notation, let's go ahead and do that right up here so that we can see our number line. F is increasing whenever this is positive. So it's increasing from negative 1 to 0 and from 2 to infinity. F is decreasing from negative infinity to negative 1 and from 0 to 2. And that's the answer to this problem. Now you might think that, well look, these signs are just alternating. I don't have to actually plug in all those points. I'll just plug in this first one and then I can just alternate the signs. Well, that is a really bad idea because it turns out that there are lots of functions where this isn't actually the pattern. There's lots of functions where it is, so you might be tended to think that that's always the case, but it's not. So you want to always make sure that you test points in f prime in each of these intervals.